Okay, this section we're going to be looking at independent versus dependent events. We'll get into the difference between those in a second, but I want to talk about the difference between this section and last section first. Last section, you were dealing with basically one item, one person, one thing, and that one thing or person could take the value of two different things at the same time. So for instance, we were dealing with like finding the probability that a person is a male or a sophomore in high school. The probability that a person is a male or a female. The probability that a t-shirt is red or white. Okay. We're talking about one single person, one single t-shirt at a time. This section we're going to be looking at the probability of picking like two people at a time. And I mean, we'll pick them, pick one and then pick the next one. But in the grand scheme of the problem, it's going to be like two things at the same time. Two events is what we're going to be calling them. The event being picking one person and then picking a second person. We're picking one t-shirt and then picking a second t-shirt. Okay. Sometimes we'll even get into 3 or 4 events, but for right now, just as your basic explanation, we're going to talk about just 2 events at a time. Okay. So, independent versus dependent. 2 events, we're going to call them A and B, are independent if the fact that A occurs does not affect the probability of B occurring. So, for instance, if you roll a die and pick a card out of a standard deck of cards, those are independent events. The reason being, whatever happens, the probability of your first event, rolling a die, if you roll a 6, that has absolutely no effect on whether or not you'll pick, say, a king from the deck of cards. Okay? Doesn't matter if you roll a 1, a 2, 3, 4, 5, 6, it will have no effect on the card that you pick. Okay, that's independent. Dependent is when the first event does affect the outcome or the occurrence of the second event. Okay, so for instance, if we said, what's the probability of picking a king from a deck of cards, keeping the card out, and then picking a 10? The fact that picking a king the first time and keeping the card out of the deck directly affects what the probability of picking a 10 the second time around is, because there's one less card in the deck, so your probability changes. Okay. Independent would be if you, what's the probability of picking a king, putting the card back, and then picking a 10? Those are independent because the probability of picking a 10 does not change whether the king was picked or not. And the reason is because whatever card we picked the first time was put back in the deck of cards for the second draw. Okay. If you have any questions on that, write them down. Hopefully the next few examples will kind of help clear some of that up. Because there are 2 separate, 2 different ways that could be calculated, we got 2 formulas again, just like with the with the probability of A or B. Probability of A and B has 2 separate formulas. One thing to remember, and is multiplication, or is addition. Okay? So if the events are independent of each other, it's as easy as just taking the probability of A times the probability of B. However, when your events are dependent on each other, you have to take the probability of A times the probability of B, given that A occurred. So, one thing I want you to make sure, that right there does not mean divide. What it does mean it means given that. Okay? what we're talking about is, let's say we have the probability of picking, let's stick to that. Let's stick to the example I talked about. Probability of picking a king and a 10. Now, we will not replace the card, okay? So to find this, we say, what's the probability of picking a king times the probability of picking a 10, given that a king was selected. So, what's the probability of picking a king? 4 kings, 52 cards, right? What's the probability of picking a 10, given that you know a king was selected the first time? Well, how many 10s are in the deck? There's still 4 of them. How many cards are left? This time there's only 51 because that king was kept out. And that's what changes. Okay, that's why this number is a little bit different, because this was dependent on that. Okay. A coin is flipped and a die is rolled. When you encounter these problems, always try to decide, is it independent or dependent first off. Okay. The other thing is, going along with the last section, is decide if it's an and or an or problem. That'll help you kind of start off. So we're right now we're talking about a coin is flipped and a die is rolled. So we're looking at our and formulas. Then you have to say, is it independent or dependent? Does flipping a coin and say getting a heads, does that have a direct effect on how you will roll a die? And the answer is no. So those are independent events. So it's as simple as saying, what's the probability of a head and a 4 is the probability of flipping a head times the probability of a 4, rolling a 4. And a head is 1/2, a 4 is 1/6. Multiply them, you get 1/12. Now you may say, well, why can't I just do this using a sample space? And you can. If you would have come up with your sample space by doing a tree diagram, saying you could have gotten a heads and a tail. Once you got a head, you could have gotten a 1, a 2, a 3, a 4, 5, or 6. And then your sample spaces were head 1, head 2, head 3, head 4, and so on. And there's only one way to get a head and a 4. Next up, a Harris poll found that 46% of Americans say they suffer great stress at least once a week. If 3 people are selected at random, find the probability that all 3 will say they suffer great stress at least once a week. Thing to think about this is it independent or dependent? And you may say, if we select one American, there's one less American pick the next time around. When you're not given the exact numbers, and the next example will show you that. When you're just given a percentage for an example like this, you need to assume that they're independent. And the reason for that is, I guess, you don't know how many Americans there are. There could be so many that picking one American doesn't change this percentage. Like it affects it so small that it has no effect on it. So doing something like this, when you're not given the full sample size, you're not told how many Americans we're looking at, you need to assume that these are independent. So the probability of picking somebody that suffers stress and stress and stress, so 3 separate people, right, is the probability of somebody with stress times the probability of someone with stress times the probability of someone with stress. So that's 0.46, 0.46, 0.46. Multiply them all out and you get 0.097. So you have about a 9.7% chance of picking 3 separate people and all of them say that they suffer great stress at least once a week. This is an example of where it is dependent, and it's because we're given the exact numbers. So, University of Western Pennsylvania, we're looking at 5 burglaries reported in 2003, 16 in 04, 32 in 05. I want you to think of these as like case files sitting on a desk. So there's 5, 16, 32. That's 53 separate case files. They want, if you pick 2 of them at random, don't put them back. So you pick one of them, keep it out, pick a second one. Find the probability that both will have occurred in 2004. So what this is this is the probability of picking one from 2004 and 2004. So this is the probability of 2004 times the probability of 2004 given the first one was 2004. So what we do is this. The probability of picking a case from 2004, there were 16 of them out of a total of 53. But once we pick that one, there's now not 16 from 2004 anymore. There's only 15 of them. And there aren't 53 total files. There's only 52 of them. So that's what this part turns into. That's how this, what's the probability of picking a case from 2004 given that the first one was 2004? That's how this changes. Reduce that fraction if possible. This one is not, or write it as a decimal. That's 60 over 689. Conditional probability. What if you're asked to find this? The probability of B given A. The formula for that is the probability of A and B divided by the probability of A. So what's the probability that Sam parks in a no parking zone and gets a parking ticket? Or the probability, sorry, that that happens is 0.06. The probability that Sam cannot find a legal parking space and has to park in a no parking zone is 0.2. On Tuesday, Sam gets to school, has nowhere to park except a no parking zone. What's the probability that he will get a ticket? The hardest part is writing it out in words first. So to make that easier, a lot of times we'll just use a single letter to represent something. When you do that, make sure that you write this down so that I know what N and T stand for. Okay? Don't make me guess. When I have to guess, sometimes I get it wrong, and that causes you to get points docked. So make sure to write this out if you're doing this. So what's the probability that he will get a parking ticket given that he parked in a no parking zone? That's the probability of N and T divided by the probability of N. The probability of N and T is 0.06. The probability of N is 0.2. And that comes out to be a 30% chance that he will get a ticket if, or given that, he's in a no parking zone. Okay? Here's another one. A recent survey of 100 people asked if women in armed forces should be permitted to participate in combat. The results of this survey are shown right here. So what's the probability that the respondent answered yes, given that it was a female? So again, what's the probability of being a yes? Here's an example where I understand that Y is yes, F is female, but when it's more than that, when it's more than like a single word, you got to write it out for me. What's the probability that you answered yes, given that it was a female? That's the probability of a female and yes. So females, yes, there's 8 of them out of a total of 100. And the probability of being a female is 50 out of 100. Now what you can just do is you get rid of those 100, and that turns into 8 over 50, which reduces to 4 over 25. Sorry, I got interrupted one more time. 2 more examples left. Find the probability that a respondent was a male given the respondent answered no. Again, what's the probability that you have a male given that they answered no? What it's really saying is just look at only the people who answered no. And you could just think, all right, we're only looking at people who answered no. So these 60 people, what's the probability that they were male? That's 18 out of 60. So you could do this if you were given the sample space without going through the formula, but I want to make sure that you're comfortable with the formula because eventually you're not always given the sample space, okay? So we find the probability that they answered no and they're male. It's 18 of them out of 100. And the probability that they answered no is 60 out of 100, which reduces to 18 over 60, which reduces to 3 over 10. Last one. So this is an example of what I was talking about if there's more than 2 events that happen. So the Neckwear Association of America reported that 3% of ties sold in the U.S. are bow ties. If 4 customers who purchased a tie are randomly selected, what's the probability that at least one of those people purchased a bow tie? Now you can do this a couple of different ways. The long way is finding the probability of one person Purchasing a bow tie, the probability of 2 people, the probability of 3 people, and the probability of 4 people, and then adding all those up. But if you think about it, what are your options? Out of 4 people, it's possible that 0 of them, 1 of them, 2 of them, 3 of them, or 4 of them purchased bow ties. We are looking for this group. Okay? So like I said, you could find 1, 2, 3, 4, add them up. Or if you know, what's the total, like the probability of all 5 of these added together has to be 100% or 1. Well, what if you just found the probability of this guy and took it away from 1? That's way easier than finding these 4. And that's what we're going to do. So the probability of a bow tie is 0.033%. The complement, which would be the probability of not wearing a bow tie or purchasing a bow tie, is 97%. So basically, we're finding 0 people, probability of no bow ties out of 4 people. So that's the probability of the first person not buying a bow tie, the second person not buying a bow tie, the third, and the fourth. So you multiply all those out, and you get there's an 88, like 0.885 or 88.5% chance that nobody will purchase a bow tie. So if that's what this is, 0.885, all these others added together have to be 1 minus that answer, which is 0.115.